Okay, so in this video we want to look at odd or even functions. The heading really here should be odd or even functions. Since a function can't be both odd and even, it's going to be either odd or even. And the important thing, which we'll talk about as well, is it doesn't have to be odd or even. It could be neither odd nor even, but it can't be both odd and even. So a function that's described as odd has the following algebraic property. F of negative x is equal to negative f of x. So for example, we can show algebraically that f of x equals x cubed minus 2x is an odd function. So if we work out what f of negative x is, which means replacing all the x's in f of x with negative x's, okay, and we tidy this up. So negative x all cubed is negative x cubed, because negative x times negative x times negative x is negative x cubed. And then negative 2 times negative x is positive 2x. And then if we were to factor a negative out from here, we get negative x cubed minus 2x. Now x cubed minus 2x is our original function. X cubed minus 2x is the original function, and so all we end up with here is negative f of x. So algebraically, we're able to show that f of negative x is the same as negative f of x, which means that this is an odd function. We can also consider the graphical implications of this relationship. So here's the graph of x cubed minus 2x. It's got 3 x-intercepts. It's this fairly traditional cubic kind of shape. And let's have a think back to, and I know we haven't looked at any transformations this year, but hopefully these are fairly familiar transformations. Y equals negative f of x is f of x reflected in the x-axis. Okay, it would look like f of x after reflection in the x-axis. Whereas f of negative x is f of x after reflection in the y-axis. So when we have odd functions, we're seeing that these two things, negative f of x and f of negative x, are the same. So the graphical implication of that is that if a function is odd, when you reflect it in the x-axis, you will get the same thing as if you had reflected it in the y-axis. So if we think about reflecting in the x-axis, this point, this point goes down to here, this point comes up to here, this point stays here, this point stays here, this point stays here, this point comes down here, this point ends up here, and we end up with that. Okay. If we reflected it in the y-axis, this point goes over here, this point goes over here, this point goes over here, this point ends up over here, and we again end up with exactly the same thing. Okay. So the blue graph, we thought about reflecting the graph in the x-axis. The purple graph, we thought about reflecting the graph in the y-axis. And we've ended up with the same thing. And so, yes, that is the case here. Reflecting this graph in the x-axis gives the same result as had we reflected it in the y-axis. And so algebraically that means that f of negative x is equal to negative f of x, which by definition makes this an odd function. An even function has this algebraic property. F of negative x is equal to f of x. Okay, so we can show, for example, that this particular function here is an even function. So we want to again work out what is f of negative x. So that is replacing all the x's with negative x's. Okay, so we get negative x all squared minus 4. Negative x all squared is still just x squared. So we end up with x squared minus 4. And x squared minus 4 is the original function. So f of negative x is just equal to f of x. So definitionally that makes it an even function. So again, graphically we know that f of negative x is f of x after reflection in the x-axis. Sorry, in the y-axis, my apologies. So what this is saying is that the reflection in the y-axis is equal to the original function. So i.e. something's an even function if when you reflect it in the y-axis, you still get the same graph that you started with. Okay. So if when you mirror in the y-axis, nothing changes, i.e. if the graph is symmetric about the y-axis, it will be an even function. And so this is indeed the same here. We have symmetry about the y-axis. And so that makes the function an even function. As I said before, it's important to note that a function does not have to be odd or even. Okay, it's quite possible. Sorry, that should be or. A function does not have to be odd or even. There are many functions that fit neither definition. Okay, so it's quite possible that when you work out what f of negative x is, that it doesn't end up equaling negative f of x, nor does it end up equaling f of x. And so therefore it's neither odd nor even. Okay, let's just have a look at one example here. Determine whether f of x equals x minus 2 squared times x plus 2 squared is an even function, an odd function, or neither. Justify your decision. Now, my instinct's just looking at this function. It's a degree 4 polynomial. It's an even degree polynomial. Now, not all even degree polynomials are even functions, but I can assure you it's not going to be an odd function. It's either going to be an even function or neither. So let's just be clear about that. So you could have a quartic, for example, that does this. That's a perfectly fine quartic. It's not symmetric about the y-axis. It wouldn't be an even function. Okay, so it's important to understand that. Similarly, you know, the nice cubic we looked at was nice and symmetric, so that if we reflected it this way, we got the same thing as if we reflected it this way. But there's plenty of cubics, you know, draw it up over here. If we reflect that in the x-axis, it's going to look something like that. If we reflect that in the y-axis, it's going to look something like that. They're not the same. It's not an odd function. So please don't just assume odd degree polynomial, odd function, even degree polynomial, even function. However, an odd degree polynomial absolutely will never be an even function. It's either going to be an odd function or neither odd nor even. So if this is a degree 4 polynomial, I'm pretty sure, I'm 100% confident it's not going to be an odd function. It's either going to be an even function or neither. In both instances, when we're testing for even or odd, we want to think about what happens when we do f of negative x. Does it equal negative f of x, in which case it's an odd function, or does it equal f of x, in which case it's an even function, or is it neither of those things, in which case it's neither odd nor even? So we want to work this out. So it's going to be negative x minus 2 all squared. So all I'm doing is replacing all the x's with negative x's, and negative x plus 2 all squared. Okay, so we want to try and turn it, given I think it's not going to be odd, it's going to be even. I want to see if I can turn it back into that original function. So if I think about factoring out a negative in here, and again factoring out a negative in here, and now that's essentially negative 1 times that bracket. So we've essentially got negative 1 squared times x plus 2 squared times negative 1 squared times x minus 2 squared. The negative 1 squareds are just 1, so it's just x plus 2 squared times x minus 2 squared, which is f of x, the original function. And so therefore, since f of negative x equals f of x, f is an even function. Okay, so again, you know, being clear about the reason by which you know that it's an even function. Here's the algebra to support that. That's showing me that f of negative x is equal to f of x, which means that it's an even function. Okay, we can test that using CAS. So if you defined your function, menu 1.1, if we defined our original function, f of x is going to be, now a couple of people don't like, so when I started typing that, the f has come up as bold. That's because previously I defined a function as f of x, but that doesn't matter. If I'm now defining f of x again, this new definition will just overwrite the old definition. So you don't need to delete, rarely do you need to delete the old definitions, you just keep overwriting them. Okay, so that's my function. If I want to test whether it's an odd function, I would just type f of negative x equals negative f of x, and it just gives me an expression. It's just made those two things equal. So it means that that's not all. It might be true sometimes. For some x values, that relationship might be true, but it's not true all the time. Okay, I would have to solve this equation to find what x values that's true for. Okay, whereas if I test whether it's an even function, so f of negative x equals f of x, which we know it is from what we've just done by hand, if it says true, which it does, it's saying true because this relationship is true for all values of x. So therefore, this is a completely true statement. It's not just an equation to be solved. So you're looking for it to say true to justify that it is an even function. If, for example, we defined f of x as being equal to x cubed, which is the simplest, no, not the simplest, it's a simple odd function. This time if I typed, I don't even need to retype it, let me go back up here. If I just do f of negative x equals negative f of x, in that case it'll tell me that's true. If I were to try to test that it was an odd function, oh sorry, it's the same one. Sorry, if I was trying to test whether it was an even function, it would just give me a relationship. No, this isn't always true, but it is true for whichever x values make that equation true, which would be 0. It would be true. You could also have, for example, if we define another function, let me make it another cubic, but let me make it x minus 2 all cubed. Oops, cubed. If I try and test whether that's an even function, no, not an even function. If I try to test whether it's an odd function, no, it's not an odd function either. So it's neither odd nor even in that instance. Okay, so the work today is from exercise 1C. That list of work encompasses work on both piecewise functions and also on odd and even functions.